Okay, welcome to this video on electrochemical cells and electrode potentials. The main things we're going to look at are the IUPAC notation of cells, calculating the EMF for cells, and explaining if a cell is feasible. Okay, so you may have seen these already. Different electrochemical cells. If you've got two metals being connected together, or you could have a gas and a metal being connected together, so gas half cell. In this case, on the left hand side it's the standard hydrogen electrode, and here we're just trying to measure the EMF of the zinc particular sign electrode potential. Or you could use metal ions in solution, such as the Fe2 plus and Fe3 plus together, again using an inert platinum electrode. Okay, now the main part of this is the electron flow in cells. So electrons will always flow from the negative electrode, the cathode, to the positive electrode, the anode. So at the negative electrode, electrons are generated. So if we're generating electrons, how are we doing it? Well, atoms are losing electrons, so we're creating ions. So if atoms losing electrons, that is an oxidation process. Conversely, at the positive electrode, once the electrons have flowed through the wires, the electrons are used up, they are consumed, i.e. ions are gaining electrons, forming atoms, and we all know that the gain of electrons is reduction. Now, there is an IUPAC standard notation to represent these electrochemical cells. Here are three different examples showcasing different aspects. Here's the fairly standard cell notation of a metal with metal ions on both for each half cell. The double line in the middle is the salt bridge, and a single line represents a phase boundary. So that will be a solid, that will be aqueous, solid. If we got a gas, such as hydrogen for the standard hydrogen electrode, then we need to include the platinum electrode as well. That separates, so the platinum is separated from the hydrogen, that's in a different phase to the hydrogen ions. Okay. On the other side of the salt bridge, we've got a lithium ion, lithium half cell. Alternatively, if you've got a electrode potential being set up between two sets of aqueous ions, then you separate those aqueous ions with a comma, and then you show the platinum electrode here. Chlorine can be sometimes given in questions as being either as a gas or aqueous state. So here, because I've separated the chlorine and the chloride with a comma, then I'm showing the chlorine, I'm indicating that the chlorine is aqueous at this point. Again, we've got two platinum electrodes here. One thing that might be catching your eye is we've got the charged ions near the salt bridge here, on this side, but we've got the chlorine gas here next to the salt bridge rather than the chloride. Okay, and so this follows all of our rules, which I'll show on the next page. Yes, so the vertical line represents a phase boundary, so it separates what's like a solid, a solution, or a gas. Species which are in the same physical state are separated by a comma. We saw that. And a double vertical line represents the salt bridge. We saw that as well. Now, the species with the highest oxidation state is written next to the salt bridge, i.e. the most positive value. So here in the example of chlorine and chloride, chlorine has an oxidation state of 0, chloride has an oxidation state of -1, so chlorine is the most positive. The standard hydrogen electrode, by convention, is always written on the left-hand side. And when we're writing cells, we should put the oxidation process on the left-hand side and the reduction occurring on the right-hand side. So let's exemplify here. So we've got the zinc 2 plus ions, copper 2 plus ions, copper, 2 half cells connected together. So the zinc's on the left-hand side, copper's on the right-hand side. On the left-hand side, oxidation is occurring. That's the rules. So therefore, by default, on the right-hand side, for the copper, a reduction process is occurring. Because oxidation is occurring here on the left, we can identify this as being the negative electrode. The right-hand electrode is the positive electrode. So I like to think of this, I remember this as LON, left oxidation negative, and RRP, right reduction positive. Now, how do we assign which half cell will be the negative electrode, which half cell will be the positive electrode? We have to look at the electrode potential values, and the one which is most negative will become our negative electrode. The one which is the most positive becomes our positive electrode. Okay, so if we look at the two electrode potentials in this system, the zinc 2 plus gains 2 electrons to make zinc. It's got electrode potential of minus 0.76 volts. Conversely, the copper 2 plus to make copper has an electrode potential of plus 0.34 volts. Okay, so you can see here that the zinc 2 plus zinc electrode is more negative. So how would we go about calculating the EMF of this cell? So here's just a reminder of our values. We use this formula. The E cell, or the EMF of the cell, is equal to the electrode potential for the oxidation reaction plus the electrode potential for the reduction reaction. So, for the reduction reaction on the right-hand side, we've got copper 2 plus gaining 2 electrons to give copper. So we know that is plus 0.34 volts. But to find the electrode potential for the oxidation process, i.e. zinc losing 2 electrons to make a zinc 2 plus ion, we need to reverse this equation, this top equation, and by doing so we reverse the sign of our electrode potential. Okay, so then a question we might ask, does zinc reduce copper 2 plus ions? And so we'd have to work this out. And so if you look at the EMF of the cell, so the oxidation electrode potential is now plus 0.76 volts, and we're going to add to that plus 0.34 volts, which gives overall an EMF of plus 1.10 volts. Always quote to 2 decimal places. And so to answer the question, does zinc reduce copper 2 plus? Well, because the electrode or the EMF of the cell is positive, it's greater than 0, the reaction is feasible. Okay, how do we answer this question though? Does zinc reduce the copper 2 plus? Well, yes it does, because the electrode potential for the copper 2 plus / copper is more positive, or is greater than the electrode potential for the zinc 2 plus zinc half cell. Okay, and that's all you have to do. You just write the chemicals out in order. So the left hand side chemical, Cu2 plus slash the right hand side chemical. Another example you might be given is something like this, where in actual fact the cell notation has already been given to you. So you have to calculate the EMF for that cell. So here we've got silver and silver ions on the left hand side. We've got copper 3 plus chromium 3 plus chromium 2 plus on the right hand side. So LON, left hand side oxidation, negative electrode. RRP, right hand side reduction, positive electrode. So here are two reduction potentials, and we have to calculate the E cell by saying the electrode potential of the oxidation plus the electrode potential of the reduction. So in this case, silver will be oxidized to silver plus ions, so we need to reverse this equation and reverse the sign. So that will give us minus 0.80 volts. We're going to add to that the reduction potential, which is minus 0.41 volts. So that will give us overall an EMF of minus 1.21 volts. So therefore, no, chromium 3 plus cannot oxidize silver. And we would say, because the chromium 3 plus chromium 2 plus electrode potential is less than the silver plus silver electrode potential. Okay, final example. You might be asked, you might be given a couple of equations and like this, and asked to calculate the overall EMF of the cell and write an equation for what's going on. Okay, so first of all, you've got your two sets of values. Identify which is the most negative electrode potential, because this will become our oxidation reaction, i.e. our left-handed electrode. And so the iodide is the most negative, so we know that this would be reversed, and this will be the equation we're looking at. Write the cell notation. Again, I'm just assuming that the iodine and the chlorine are aqueous at this point, just for simplicity's sake. So we're separating the iodide and the iodine with commas, same for chlorine and chloride, and we're using our platinum electrodes. And then we need to calculate the E cell, where we've got the electrode potential of oxidation plus the electrode potential of the reduction. So that is minus 0.54 plus the positive 1.36 gives us a value of plus 0.82 volts. Okay, so that would be the expected electrode potential at the EMF of that cell under standard conditions. We also have to write a balanced equation, and so to do that we need to balance out this equation, remembering that no electrons should be shown in this overall equation. And so here's our oxidation equation, here's our reduction equation, and when we combine the two together, the two electrons both sides cancel out. Obviously, if we had an uneven number of electrons in two cells, then we would have to multiply one or both of the equations up to get the correct number of electrons so they could cancel out. Okay, thank you for watching.